Alright, just waiting for it to go live. Alright, so appears that we're live. Okay, so welcome back to another stream on the ROS2 powered robot with the Raspberry Pi 5. So in the last stream, when we designed the logic board for our robot, and realistically the logic board's fairly straightforward because we're using motors that have a speed controller already built into the motor. Realistically, all we have to do is build a breakout board that attaches our Pi Pico chassis microcontroller to all of our sensors and the motors, and also provide just a small bit of logic to control the drive motor of our LiDAR, and then also hooks up to our voltage regulator. So today what we'll be doing is, again in the last stream we finished soldering together the motor drive component of the whole thing and the voltage regulator. But we did not get the MPU, the IMU soldered in, or the LiDAR control stuff soldered in. So today what we'll be doing is finishing up the soldering for the logic board. And I was thinking of doing this off stream, but like the whole point of this stream is to, not much research was done off camera. So and not much building was done off camera. You know, the idea is to provide everybody with a holistic view of how long this kind of stuff takes. So, and walk you through the whole process. Walk through this whole process together. So, I am going to flip the camera over to the desk cam, and we're going to finish soldering. And so, again, the only thing that we have to do is we have to finish soldering the IMU in, the LiDAR drive in, and the camera servo connection in. And then we'll be done with the chassis board. And then we'll be able to move on to 3D printing all of the mounting jigs, but we'll do that in the Tuesday stream. And we'll also we'll also verify everything works today, because we can repurpose the IMU yaw control code from the balancer, which we're already repurposing for now anyway. But we won't do the LiDAR until probably 2 weeks from now, because we'll do the 3D printing next week, and then we'll do 3D modeling, 3D printing next week, and then the following week we'll be doing code, or we'll start getting into the code. And so without further ado, I'm going to turn off the webcam, and I'm going to flip the camera over to the desk cam. Alrighty, let me flip over to George. I'm still here, we're just trying to type in Droidcam on this phone. Alright. Hopefully it's starting to come up. And I think it'll look all inverted for y'all, so let me mirror and flip. And hopefully... Alright, let me try to straighten out the view here. 3 feet base. Okay. So, turn on the light here. Alright, let me flip the microphone over to the phone, which is unfortunately quite crunchy, but we will put up with it, right? Alright. Looks like we're broadcasting audio and the camera's in the right spot and everything. So, gonna have to take apart, unfortunately take apart the robot again, even though it took us a little bit of work to get this in. So let's grab this from last time, pull out our logic board, there. Really wedge that thing in there. Okay. There we go. Now we shall unscrew the terminal block. Okey-doke. Disconnect our motors without breaking the wires like we did that other time. All right, logic board back out. Set the robot aside. Okay, pull our Pi Pico out. Okay. Perfect. All right, fine. We gotta pull out the next smallest one because we gotta get our 3D printed bracket here off. All right. All right. Perfect. Set that aside, and we shall, oops, not bump the camera, and, okay, it's still off. We're going to switch the soldering iron tip back out for the one I like to use. Which is just a good old wedge tip. To avoid touching the iron as much as possible. And we shall put the iron back in there, heat up the iron. And all right, so I think we're going to start with the IMU. And what we're going to be doing is using this low profile connector on the board. And like these, we're going to mount it on the back side just so we have more clearance to do stuff. We're going to try to get it into the center. But I think actually in order to do that, I'll leave this pin header installed actually, because that'll give us, that'll stick through the board and make it easier to mount. So let's actually try to put this in the center as much as possible. It's not going to quite center, unfortunately. Oh, I need to reset the iron's temperature because we were using it for heat set inserts. We get back up to 720 degrees American, Fahrenheit. And then we'll do, which I think is around 400 degrees Celsius. All right, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 on that side. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, wow, we actually got it centered on the first try. Okay, so. Okay, so it's just one over from the end of the Pi Pico connector. So we'll remember that, and we'll put down some flux in order to make sure that we can get this to stick. Stick well, anyway. Right. So otherwise solder won't flow very nicely. Just make sure this slides into there. Oh, I did that quite the wrong way. Okay. Okay. Soldering in the the power for the Pico made this a little more complicated, but okay. So let's go ahead and clean our iron, bring our solder over. Put our iron over here. So we'll do connect this one, and we'll connect this one. All right, that locks those tabs down. So we can flip the, now that we have that, we can take the connector back out. Go. I'll just put the thing of electrical tape under it just to give it a good lift so I can see it better, because the sun's in my eyes on the right. But whatever, I suppose. Things we do.
Is that well connected? Probably not, but the middle one certainly isn't. Okay. Well, once we start putting things through the top, it'll get better here. Interesting. Okay. There we go. It's connected. All right. This one. This one. Do that one. Okay. And that should have soldered. Well, almost anyway. Let's. All right. Perfect. Looks like all the little tabs are connected. Which is great. All right, we've got our IMU connector put down, which is wonderful. All right. Again, if anybody has any questions, just put it in the chat. I'm going to try to check my computer from time to time to make sure I answer any of y'all's questions. All right, so got that down, and now we got to decide which way we want to actually solder this connector onto the IMU. Because remember, this thing is mounted when the robot's this is installed in the robot. It's the black connectors are towards the top, so it would be mounted in the robot like this. So if we could put the connector upward facing, and that would allow the IMU to sit in like this. Because what we're trying to do is make sure that the IMU is parallel with the plane of the robot versus being at an angle, because we're gonna, at least initially, we're going to use the DMP stack inside the MPU-6050, and I don't believe it particularly appreciates being outside of its natural axis alignment. So we're going to try to keep the IMU vertical. We're going to try to keep the IMU parallel to the plane of the robot, so horizontal, not vertical. And so we can either do it this way, and remember we've got this connector along the bottom. So we'll actually be remodeling this in the next stream, where we'll put the mount. We'll bring up some like mounting posts from this to the IMU, and so that's one option. The other option would be to mount it further down, and I just want to make sure I have enough space, because that's really the only constraint here. Looks like it might be fine, actually. If we wanted to make it mounted downwards, then we could do this way. Oh, part of me thinks that's not going to work. Yeah, that's not going to work. It's not, well, actually, it might just if we cut off the slack on the connector. Because remember, if we actually flush cut this thing, it might work. But that if it weren't flush cut, if it were flush cut, it might just work. That involves getting our flush cutting perfectly. That actually might be real nice, just from the perspective of if it sits in there like perfectly, then you know what? I do have an extra FU 6050, so if this really doesn't work, we can always just do something else. But we can also cut out the connector space immediately under it and just let the rest of it sit flush. So let's actually try that. So we'll, all right, so let's flux up the connector for here, and then solder this in. All right, that's one. I need to bend this a little bit, so while not burning myself anyway. Try to realign this connector slightly. It's always a fool's errand, really. Yeah, didn't quite get it right again. We're just trying to make this as flush as humanly possible. That might be it. I got it. Not quite. Okay. Maybe this time. That looks about as perfect as I'm going to get it. So let's tack the rest of them down. And so before we let's do this side. Just go A B A B A B to keep the heat down. All right, perfect. And so now what we're going to do is go in with the flush cutters. Try to cut these pins down to the exact flush with the board. That might actually work. They're rocketing off quite fast, so it kind of hurts. Okay. And then we'll got a couple more to do. Ow. Those aren't quite perfect. Just going through here, touching these up. Ooh, I hit the edge of the board on accident. That's fine. There's no traces right there. Alright. But I got it. Okay, perfect. So now let's see how well this sits flush. With our flush cut. Alright. Do this. And it looks like that didn't quite work. Actually, it looks like it didn't quite work because of this freaking this other thing here. This wire. All right. Let's try lining this again. Yeah, I'm not a huge fan of. Oh, actually, it might. Nope. It worked. It actually worked. We're good. It's just flush enough. Perfect. Okay, we got it. That's perfect. We got it. Alrighty. I love it. And also we can shorten this by 0.25 millimeter or so, and we'll make it align. Or I mean, we can actually just cut a groove into it in our slicing software, so I'm not really too worried. We'll just do a U shape out of here in the final version, right? Okay, so that's fine. Now we actually can wire that thing up. Leave the socket there. Next thing we got to do, the only other two things we got to do is we got to put in a servo drive connector, and we got to put in the transistor driver for. We got to put in the motor drive for the LiDAR, and so we can probably hook that stuff up over here. Well, actually, I don't know if we can hook that stuff up over there. It might not fit. Okay, well, I mean, it'll fit if we, because we want the 12 volts to come down to the transistor to build the motor driver. So we actually might just leave the motor drive over there, and we could probably put the servo connector. Where's the? Might just put the servo connector over here. We could also put it here. I mean, it's not really sensitive. Oh yeah, we could put it right there. Keep it, actually, maybe we put it, because I think I took the servo pin is over here. So, I mean, we'll figure out where we want to put it. And we also need to place the, LiDAR data connector, but we'll do that in a second. Let's build up the LiDAR motor drive circuit first. So the negative rail is the one closest to us, so we'll actually put the negative side over here. If we look at the pinout of the motor of the LiDAR's drive motor here, we can see that effectively what represents pin 2. So we're counting from the left. Pin 2 is we have this backwards. So we want the little locking tab to go out towards the connector. And then what we'll do is put, actually no, I take that back. We want the 12 volt side to be close. Right, the motor's high side. I apologize. I'm sorry, I'm wrong. So yeah, we want it to look like this. Sorry, we want because the transistor's below the motor and the transistor. So let's look at the pinout diagram for this. So the pin 3 is the collector. The collector is what's going to go up against the motor. And so the collector is pin 3. So if we look at the transistor from the bottom, pin 3 is this one on the side. So this is, so we'll just pull those two over. So the one that's separated off right now is pin 3, which is our collector, which is the top side of the transistor in the schematic. So that'll be where we want to connect the input of the motor to. So let's tack down this connector for the motor and wire up the 12 volt side, and then we'll put in the transistor. Let's reheat the iron, and then we'll put some flux down, some finger. All right. As the iron heats up, we'll just get a little bit of solder on it. Hopefully we'll be able to put this connector on without burning myself here. There we go. Oh, is it stuck down enough? Nope. There we go. Now it's tagged or whatever. Okay, so we can now, perfect. We can now solder the other side. We now do a good job of soldering the other side, and then fix the soldering on the first side. All right. Perfect. Nice. Perfect. All right, so now we're gonna need, okay. So we do there. And then we need to add our signal diode across the motor. And remember, we want to do it in reverse. So we want the bar on the white circle on the diode corresponds to the cathode on the diode. So that's the side that's the bar in the schematic. So we actually want that to go vertically towards the 12 volt side. So we'll just do this diode in the classic fashion of vertically mounted. So we'll do that. We'll just bring this over. All right. And then we'll put it up against our motor here. All right. There we go. Just lay these out so we lock it in place. All right, our diode's in. This is the flywheel diode to make sure that current spikes don't escape too much. Just untangle this soldering iron cord here. All right. Put that down. And then what we're going to do is drag this lead over to the motor side, then drag this lead over to the motor side. We'll actually use this lead. Actually, I did that a little backwards. Sorry. Well, yeah. Do that, and then I think what we're going to do is we're going to try to use this lead to connect us up to the up to 12 volts. So we'll bend this. Actually, we'll do the soldering first, and that'll let us bend it to our heart's content here. Oops, sorry for the bump. Bridge, do this bridge. Nope. Okay. There's too much solder on that one. Okay. Okay. So we're gonna flush cut this. We're going to try to do is drag the this wire around. Now that's still kind of hot. Drag this lead around and use it to try to form our connection to 12, which isn't going to quite make it. But what we can do is solder ourselves up another lead here. Using one of the old legs, one of the legs of the diode, and we can ensure that we have something to mount to on the other side. Pull the iron back, get some solder. Let's stick this over here so there's something off of. Let's grab those third hands that we had from the previous room. Be a good use of them right now. As we don't accidentally solder our third hands. Just all right. that done. I don't know if it's done particularly well, but let's do the bend over here. Snip right there. I snipped the wrong one, but that's fine. Damn it. It's fine. Okay. But they still line up. Okay. Okay. Well, anyway, that's connected now. And now we gotta shore up this side just to make sure we got everything. Yeah, there we go. Cool. We connected our 12 volts. Check comments. Nope, we're got no comments. All right. So we've got the 12-volt side of our motor drive connected, or the positive side of motor drive connected. It's got a pretty good ground gap over there, and then now we need to do the transistor. And as we said before, this side is bent out here. Pin 3 is the collector, and that's what's going to go to our up to the motor. And so we'll just plug this in like so. That. All right, cool. We've got that. Perfect. All right. All right, perfect. That side down. Okay. With all the sides down. Nice. All right. Just gonna do a little flush cut on that. On that. Let's leave that one just for now. Okay. And just, I know I checked this before, but just to be absolutely freaking certain. Yes, we connected the right side of it. Connect the right way around. All right. Got our transistor. Now we need to bring the ground cable around. And we'll do that by we'll just do that by another Manhattan style turn here. actually, no, we won't, because that one's underneath the voltage regulator, which is not great. Okay, actually, yeah, we'll do something different. So we'll leave a little bit of lead on there just to work with. We're gonna take some, yeah, not high. The motor really not high current. I mean, motor's not really high current. So what we'll do is take a we'll take a tiny. Well, actually, I don't want to. Okay, no, that's fine. We'll take a very small key. Yeah. We'll do better. We'll do this. You don't need to do that. So I was trying to think of the gauge wire and use to bring this over to the ground site. Realistically, we don't need much. So, we'll use signal. We'll use a wire. We'll use wire wrap. It's fine. This motor pulls next to the wire. It's fine. Oh. Alright, did that. Solder that to our motor. We'll cut off this tiny piece of lead that's left. Alright. I like it. And then all we have to do is bring it over to this spot right here, because that's where the ground is. So we'll come off here. What we'll do. Actually, we want a little further up. Ah, crap. Okay, little change plan. There we go. Oh, sorry about that. Okie doke. Right. perfect. We've got our grounding system for the wire connected. Okay, nice. And now we need to add the base resistor, or the resistor on the base of the transistor, so that we can then add the control line over the microcontroller. Not sure. Well, gonna have to make some adjustments here. A little more taut so it's closer. There we go. Oh, put it backwards the way that I wanted. Transistor a little bit back. Put that in here. Alright. Come up with the excess, bend this over. Alright, cool. I'm gonna put this resistor in. That'll let us connect the base. This is the base current limiting resistor. Right. Connect that up. Right. Perfect. Snip off the excess. Well, actually, we need to flood more. Need to flood this more. Okay, cool. And yeah, now we got a good connection in there. Nice. Okay. We'll cut off the extra, and we got to check which pin we said is the LiDAR drive. I believe we said it was pin 15, but let me double check the schematic. Yes, pin 20, GPIO 15. Okay. Let's go get our signal wire again. Oh, we've already stripped it. Nice. Okay. We've got. Does it? No, still gotta get it. All right, perfect. We only have to bring it over to here. Actually, so we'll cut off some excess. Slice it right again. There we go. Perfect. Just breathe. Okay. A bit of ash on there. The ashy stuff for the most part is just burnt PCB, silk screen, and burnt flux. Not both by figure. Still looks like a cold joint. No. Shit. There we go. Alright, take it. Let's use the braid. Extra. Okay. So we've got the LiDAR's drive motor hooked up. We've got it grounded. We've got the two sets of the transistor connect. We've got the diode. So yeah, that is the LiDAR drive circuit. We have So through the motor, through the transistor, ground, through the base current limiting transistor. Yep. All right. LiDAR drive motor. The LiDAR motor driver is installed. Perfect. And we'll also need, just because of how convenient. No, actually, it's not convenient because we need 4 pins for the LiDAR data connector. But remember that there's our support crossbar. Actually, no. Yeah, the support. There's going to be a support. Crossbar. Oh wait, did I do this backwards? Oh boy, hold on. No. It sits in the robot like this. As the support crossbar would be this way. That's how I set it up. So actually, we're still not fine with putting the LiDAR connector there because of the cross brace would still be sitting behind a couple of pins, which we don't want. So we do need to put we do need to put the data connector elsewhere. And I'm tempted to place it, I'm tempted to place it over the LiDAR, the IMU mounts too, just because if we do the IMU mounting correctly, we might be able to share the space a little bit. But at least for now, I think. So yeah, we decided putting in the LiDAR like this. So yeah, let's actually start, just so we don't forget, let's start doing the soldering on the LiDAR. Not the LiDAR, sorry, the IMU. We need just to take the just to make this here. Figure grounds are there's a ground at GP, obviously. So GP2 is a ground, but then we have 1, 2, 3, 4 pins, and then another ground on the back of the 1, 2, 3, 4. Yeah, there's 4 pins facing between grounds on the pipe pico. So we could actually take a grounding line from up here. Actually, no, we can't. Sorry, I got this backwards. So ground is on this side. So it's the second pin here. We could take pin up from pi pico, or we could take a pin up this way, ground, and I could actually stick the. It could be funny. I could stick the data connector here. This is ground on the power supply. That might actually be where we're sticking this thing. Is right there. That'd be funny. Okay, I think I figured out where I'm putting it. So let's do that. All we got to do is bend out this pin, this pin. Use just a tad bit. Which we'll put the ground down. So with this, so we want basically the locking tab to go towards the power supply. Yeah, the locking tab goes towards the power supply. But we also want to hook up so we probably ought to hook up the interrupt pin of the IMU first, just in case. Which I have routed. What did I hook the interrupt pin of the IMU to? What pin did I pick? I picked IMU interrupt is GPIO 14, so right next to the LiDAR, PWM input. So that's actually quite convenient because it's also in line with what connector it needs to be hooked up to, which is perfect. Just leave that there for now. All right, so the interrupt pin. Let's take this out. We'll do the ring up here. All right. Oops, sorry for the bump. Okie doke, we'll do that, and we'll take, bend it too much and snap off the wire. Accident. Yeah. Right there. Snap off the excess. Gracefully strip the wire. There we go. Gracefully strip the wire. Broke my tweezer back over there. I did. Okay, let me grab my precision tweezers. All right. 1/4 of my workspace. Okay. There we go. Set up. Twisted the soldering connection. There we go. There we go. All right. To connect this wire. Shoot. All right. Sorry. There we go. Now we've got the hooked up. All right, perfect. And then we want to hook the. All right, so we got the interrupt hooked up. And then next thing we want to do is hook AD0 to ground, which conveniently for us is right above it. So we can just take one of these extra bits of wire again. All right. There. Perfect. Okay, cool. That's connected to ground. All right, perfect. And then, now that we got the first couple of those in here, now let's look at the LiDAR data connector, which I have pushed in some direction. Hopefully not onto the floor. There's the white thing. There it is. All right. All right. There. So put the locking connector towards the power supply. Oh, lovely. Put it right under. Honestly. All right, cool. We'll do it that way. Okay, nice. And Okay, there we go. Let's try to short these two globs together. There we go. Awesome. We've attached to ground. I think. Yeah. Attached to ground. Rocked over a little bit. That's fine. This is all prototyping anyway. And we're just trying to avoid that wire that we placed, unfortunately, a little too close, which is par for the course. And then we're going to need to tap the 5-volt rail. Yeah. And the once we do the LiDAR again, the top one is the 5-volt line. So I got to hook this this top pin here over to the 5-volt output. So again, with the absolutely microscopic tiny wire. Absolute microscopic tiny freaking wire. Perfect. All right. 5 volts. Bring that over to here. All right. Now. Tweeters. Over there. All right. All right, so we'll do that to get our 5 volts. Problem is, the moment I melt that, that wire is going to pop off, which is going to be really annoying. But if I did it real careful, like. That led to a very poor connection, of course. It's hot. Of course it's hot, it's molten metal. Okay. Low temp metal, but metal nonetheless. Alright, so that did a thing. I don't know if I'd call it a good connection or just a connection. Alright, burn zone again. It's getting worse by the moment. At least we got the wire in there better this time. Anyway, feel like I ought to hook up the 5 volts of the IMU and the servo, I guess, just because we're running out of good ways to connect to 5 volts. What we could do, we could add. We'll come back to that. I think what I'm actually going to do is split this such that this is connected on this side and the tiny wires are connected on the other side. But we do need to bring over a connector for the servo, just to make sure that we have something for the servo. Actually, you know what? We could connect, because again, 5 volts. We could. Nah. Again, it's too close. Again, I foil myself here. We'll put the servo over here. I don't really have much other good option anyway. We don't like making it so close to GPIO 1, but I don't have to. But we did use UART 0, so I don't actually mind using UART 0, or using GPIO 0 to drive the servo. Now let's do that. Let's slow this down for now. Yeah, let's put some flux on it. Hold the upper one so I don't burn myself. Yeah, of course. You know what? It might be tall enough. Oh, it'll hold itself. Okay. Perfect. Fuck, I should have done that. It's hot. Alright. Alright. Here we go. And you know what? We'll change the schematic. We'll actually use the servo PWM will be up on GPIO 0, because I mean, why not? It's up here anyway. So we'll just connect to that. And then snip off the excess. Oops. Oh, come on. Gosh darn it. It's too short. Alright. Alright. I found it. Alright. We'll do this again. Just a different length. The problem was the connection's so short that when we go to solder the other side, we remelt the heat transfers across and remelts the joint before we can get the other side down. I got it. Perfect. Perfect. Okay. Right. And so that enables us to, yeah, that'll be the servo signal connection, and we'll do, and we'll just tap the 5 volts for the servo off of that connection for the controller. Because to be honest, I don't like it being that far from capacitors, but what else are we gonna do? Okay. Oh, I need to turn on the light in this room. Oh, interesting. There we go. Turn on the lights. There we go. There we go. Check comments. None comments. Okay. No worries. So, again, if anybody has anything to ask or wants to add a comment, suggest anything, ask questions, feel free. I am trying to check them. Okay. All right. All right, let's try to merge these. Oh, shit. Ah! Ow! Okay. Bad solder joint, not a bad burn. I mean, I didn't burn myself, it's just warm, to be honest. Okay, I'm trying not to burn myself, still. Alright. Problem is, it's really hard to get these freaking wires to line up. Out. Some kind of pressure. That hurt. But now they're soldered. It looks like they're soldered pretty darn well. We'll take some flush cutters to that. Actually, I don't know if that connection's done pretty well. It actually looks like it's shifted too far forward. Yeah, dang. Okay. Well, it might be. No, I mean we got the Raspberry Pi current's coming through some of the, or the full Raspberry Pi is coming through here, so probably ought to just probably better make an effort without shorting it to pieces. It's getting worse. Every time I do this, it's getting worse and worse. Oh, no, it's not melted because I don't have the solder left on the tip. Okay. Erky Durky. Alright, that looks far better connected though this time, so we'll leave it at that. Singed. Oh, again, sorry about the camera. Alright. Okie doke. So, you got the servo signaling. Alright, we got to do the ground on the servo. That's what's left. I can actually do that pretty easy. We'll do yet another Manhattan thing because the ground on the servo can come from the ground on the Pi Pico, which is the third pin over from this side. Sorry, I think it's the same. It's the same on both, right? Ground 0, 1 ground. Yeah, we're good. Okay. Okay, cool. It's not even connected to the plug. Okie doke. Perfect. Perfect. All right. All right, cool. Did that. Right, so the servo's all hooked up now, which is good. Now got, yeah, so all we have left is to finish wiring up this IMU, and then all the soldering will be done. So, actually, we got to hook up the data connection for the LiDAR. So I believe we said it was the orange. Dang it! Sorry, I keep up the camera with my head. It is the orange wire, which is the transmit pin, which is the one above the ground connection. That's the LiDAR data line. And that LiDAR data goes to pin 17. So that'll be across the way. That's the one that didn't get connected. Ooh, it'll be fun to connect to, right? Pin 17. That's this one. That's this one under here. That's going to be fun to connect to. Okay. That's what it is. be. There we go. Right. All right. Okay, bring it over. I'm trying to put that under here. Well, snip it here because we don't need any more of that. Okay. So take this wire. Put it under here. Perfect. All right, cool. Okay. All right. That might be the most dangerous joint yet. Or not. That soldered pretty effectively, I think. Here, let me add more. Okay, cool. Cool. Looks like it's connected. Okay, cool. Cool, cool, cool. All right. Looks like we're good on that. Cool. Okay. Okay. Looks like the LiDAR transmit. Brought that over. And yeah, you know what? Let me just make sure the LiDAR actually connects to this. I mean, we're not resoldering it, but might as well see what we're up against. Well, I guess that connects fine. That connects fine. That'll do. That'll do. Ah, alright, cool. LiDAR wired. Servo wired. Just gotta finish, again, just gotta finish the IMU. Cool, we got the interrupt pin soldered, we got the address pin soldered, and then it's 2 pins for the external SDA-SCL, or XDA-XCL, which is if we want to attach the NPU to a magnetometer and have the NPU 6050 DMP core use the magnetometer. A lot of open source docs, nobody actually knows how that freaking works, so we don't have to worry about it. So the next 2 pins we're not even concerned about, and then we gotta do the ground connection, which we'll just do another little good old Manhattan thingy, because that's a ground pin on the Pico. Don't have to do anything special. It's cooling down. All right. All right. Power up. There we go. All right. All right, cool. So we got the ground wired up on the IMU. And all right, so now we need to take, all right, GND. So now we need to take 5 volts somewhere. We need to get 5 volts from somewhere. And we can do that through another tiny little I really, really, really don't want to test this joint here. Get this joint worked up again. Actually, you know what? I might as well right now just snip this connection, and then we'll resolder this right here. That'll let us Okay. That's definitely not the best connection. That's definitely. We're gonna try fixing that. It's gonna pop off when we do this, but that's fine. Connect it. Perfect. This other side. Connect that. Over here. Disconnect. And then we're gonna. There we go. All right. And all right. Okay. And we're going to take the connection from over here. Another. Another really sketchy connection. Ow, ow, ow. That's real sketchy. All right. Some conductivity. Ow, fuck. Sorry. Language. Well, that ain't. Okay. We're just suffering from a lack of solder on the tip here, which means that don't really get good connections. Okay. Okay, cool. So that wire is connected, and we're gonna bring let us bring, let me grab my tweezers again. Okay, yeah, another sketchy one. This is the sketchiest one, definitely. I'm too chicken on that one. Okay, let me see if I can get in with the tweezers. Perfect. Okay, that worked out real well. Okay, sorry, didn't say anything for a bit. We got the 5-volt connection done. We got the ground connection done. Now it's just the 2 data lines, and we'll be done. All right. So, what? Let me just check here. Comments. No. All right. So, just take a quick sip of water here. All right. Final check keycard. All right. So we want to connect the SCL pin to GPIO 13. Okay. SCL to GPIO 13. And that's going to be a. It's going to be, so that's 15, 14, ground 13. Oh, so it's another. Oh, that's XCL. Never mind. That's fine. That's fine. I thought it was going to be cruel. All right. 15, 14, 13 will go over to here. And then SDA goes to 12, right? Goes to, yeah, GPIO 12. So that'll be, so that's 15, 14, 13, 12. So it'll go just diagonal across here. So, you know, we might as well route SDA first. It's going to be a little more complicated. So SDA, that's going to be 15, 14, ground 13, 12. Okay, cool. So. All right. It's 12. And we're just going to do a snip snip right here. There's a hatred of these green resistors. And that will connect us to SDA, which is 2 over from left. Actually, huh. stadium. All right. Or wait, where's my braid? There it is. Okay. Okay, almost there. So we connected SDA, which is the fourth one. 1, 2, 3, 4. SCL. Oops, hold up. SCL I connected to 12. Hold on. No, I did this wrong. Alright. SCL, yeah, I flipped it. Shoot. Okay. I gotta undo that. Mess up. Woo. Shoot. That's not fun. Right, I did that wrong, yeah. 15, 14, ground 13, 12. 12 I just connected to SCL. 12 is supposed to be SDA. Okay, yep, it is wrong. Okay. Shoot. Okay, well. tail end of my braid. I have more. That's fine. Oops, sorry for the bump. Okay. Okay. Removed that. Okay. So, back to where we were. So, SDA, which is the fourth one, needs to get to, or sorry, let's do SCL, needs to get to SDA is probably easier to root. SDA goes to, yeah, GPIO 12. So, let's root. Yeah, sorry, that was a mistake. That was the mistake. Was rooting the wrong pin. No. We go. Alrighty. Oops. Yeah. Shoot. Alright, well, anywho. I think we melted through that. I think it can take one bump. Alright. So, do that. Do that. Hey. Okie doke, that worked. All right, let me make sure that that's not too egregious here. There we go. Okay, and that's just a filled solder hole. That's not even a break here. All right, got that. Now we can do SCL. Sure did that right. The FAR connection SDA is routed to GPIO 1514. It's routed to 12. It's routed to GPIO 12. SDA to 12. That is what we wanted. Cool. That is, in fact, what we wanted. Let's hold it here. There we go. Got one last connection to GPIO 13 for the SCL pin. Oh, I bumped the camera again, I'm sorry. All right. That will be on this side, I think. Will be the best side to do it. Because we want SCL is the third pin. All right. Some solder. All right. I don't think I actually melted anything. I don't think that actually did anything. Okay. All right. that, and then we need to route that to here. And we'll snip the wire here. Alrighty, and then trim it. There we go. All right, there we go. Perfect. All right, I think that's that. Now we've got do a little trim there. Don't care about the, yeah, so we got the interrupt, we got ground on that, we got SCL, SD, or SDA, SCL, SDA, ground again, and then 5 volts. Okay, so we're gonna plug this in. Uh-oh. And the fear is that I accidentally get some solder into one of these pins, which I don't think I did. That'd be bad. Uh-oh. Oh, shit. Yeah, well, that's what you get when you run cross beams across the pins, Nathan. Okay. Oops. Okay, that's my own damn fault. Okay, that one's fine. It's the fact that we sucked solder up into this one is what's causing problems. We'll just hike our little friend, the solder braid. And maybe, just maybe, pull solder out of the hole there. That did not work. Share. This is gonna be fun. Okay, hold up. Oh, does that mean I put solder in that hole too? Oh no. Oh no. The last thing I need is solder wicking up into the conductors. I don't think has happened yet. That is the bad scenario. That is what we're trying to desperately avoid here. Quickly just put a little solder right there. there. Gray. That didn't work. Oh, did that not work? I stripped the pad. Nice. Nice, Nathan. Good job. There's a piece of pin in there. Hold on. Okay. So that's bad. That's not good. That's very not good. Okay. Sorry. Camera again. Okay, so critical emergency here. Okay, so our Hail Mary here is going to be, I'm going to get the freshest piece of frickin' solder braid. Cut off all of this used stuff. We're gonna get a tiny bit of solder on the end here. Just do our best. That still don't work. That still don't work. Because, okay. So we're going to try a different approach. We're going to take a piece of, we're going to take one of those resistor legs. I'm going to shove it through to try to clear the blockage. So if we keep pushing, it should break. I have to get a little bit of solder in there just so we can, damn it. Right at the last second too, I did this right. Okay. Okay, one last go with the solder braid. That ain't working. Shit. Okay. Okay. Shoot, come on. I hate this. Okay. try this the other way. Maybe we try to put it to the top. And then we pull it out. Shit. Right. Hurts. There we go. Yes. Okay. We got the lead through. Doing that, we should be able to apply solder braid to the leg here. Let me get my new thing of solder braid. All right, anything solder braid. This one's a lot thinner than my old one. Okay, interesting. I think I might have got it. I think that might have done it. Or not. That could be too. I need to get some better grip here. There we go. Nice. Got it. Admittedly, I pulled the I pulled the via out of it, but that's fine because this is supposed to be a pass through anyway. There we go. It's cleared. That was not fun. Okay, let's try to do the other side now. Okay, I think we're really just gonna have to remove, actually that's fine. Just bend that up. We're going to give the same treatment to this other pad. And then we'll do the solder wick treatment to this. Which one again? This one. And of course it doesn't want to come clean. So that would be too easy. Okay. Might have to do the same dang thing as the other one. Hopefully we do that before I rip the pad off. 3, 2, 1. And bye-bye pad. Okay, that's ass. Okay, and now we'll take the other side resistor. There we go. The same old treatment. Okay. And then what we're going to do here is solder braid again. And we'll do a little bit different. We'll flood the thing with flux. Hopefully be a little more thermally conductive. The iron. And then hopefully off. There we go. Okay. Perfect. Perfect. All right, now we should be able to insert the IMU. Now we can. Cool. We can insert the IMU. It's not stuck anymore. All right. Perfect. So I'll bring the ground line back down over. Just solder ground. Thankfully there was no other connections on this side. There we go. We're grounded. Perfect. Okay, cool. Now we should be done. Okay, perfect. Now let's go through and test the continuity of some of these things, just to make sure that everything is attached as we expect. And all right. Oh my God. Okay, perfect. Oh, nice. All right, let me clean up the workspace a tad bit here. Do that, put that there. Put the wire over here. Make sure it's secured. It's also secured. All right, so let's get the multimeter. That's actually make sure we treat the iron. Just 10-hour iron. Some fresh solder before shutting it down. Right, iron off. And there, we got tree-ish. Trash. All right, push the frame, push that there. All right, multimeter time. All right, so first things first, let's make sure we didn't short the battery. As we can see, the kilo ohms are climbing as the capacitors inside the circuit charge, which means no shorts. We also have no shorts across the motor driver, although if we go in reverse, we should see a diode drop, which we do. And we should see a connection between 12 volts and the positive side of the motor, which we do. And we should see a connection between the negative side of the transistor and the negative, which we do. All right. And then on the LiDAR power, we should see 5 volts on the top pin, which we don't. Wait, sure, I'm looking at this right. Okay, we should see 5 volts on the top pin, but that's not the 5 volt connector. There we go. This should be connected, which it is. And then ground should be the bottom one, which it is. We should also see 5 volts on the center of the servo, which we do. We should see ground on the bottom part of the servo, which we don't. What? One of my leads here isn't connected very well. Oh, because we attached it to a ground lead on the Pi Pico and not the board. So unless we install the Pi Pico, we won't see the that. So let's put it on ground. Let's put it on ground. Make sure we get a connection. Yep, there we go. And now we check. Okay, so that's all the power connections. Now let's check that all of our pins are connected as we expect. So that should be the LiDAR data line, which is the orange pin, which is the second from the bottom. So if we put the probe on this one, we should see it on this pin, which we do. All right. And then for the bottom two, we should see our LiDAR base on LiDAR PWM would be the bottom one, so 14. So this should tap the resistor. Actually, yeah, so if we tap the resistor right here, we tap this, we should see a connection, which we do. We don't see it on the other ones. Yeah, no connection. And so the next one is the interrupt pin on the IMU, which, so let's try to probe the IMU pin right here. This should be the interrupt, which we can see that it is. And then 80 should be connected to ground. 80 should be connected to ground. So I'll just get my freaking multimeter on there and test it to ground. Oops, I lost my place. See that it is indeed connected to ground. XCA, XDA, XDA, XCL aren't connected, but so we got SDA should be connected to this, hold on, should be connected to GPIO 12, I believe, right? That's ground 1312, which we can see that it is. And then, just to verify, it's not connected to, okay, so that's the one it's supposed to be, which it is. It's not connected to the other one, right? Correct, it's not. We see a lot of that. So if we go to SCL, we should see it connected to, we should see connected to this one. switches. And then ground should be ground. Should be ground. I'll just get my actual probe on the pin. See that it is, or see that it is indeed. And then if we go to VCC, we should see 5 volts. Which we do. All right. So the IMU is indeed connected as it's supposed to be. And the funny bit is that this is rocking over the 4th pin. Oh, interesting. Need to lift that up just a little bit. Just a little bit. All right, cool. Now that should sit flush. And it does. Perfect. All right, nice. All right, so now we're ready to install this in the robot. So let's put our little board in again. Right, it's symmetrical, so all we got to do here is put the tabs through. There we go. Ow, fuck. Stab myself again. I'll be doing that a lot. I'll be stabbing myself. All right, put that through. Alrighty. All right, cool. We've done it. All right, perfect. Okay, we've got our board, and it is good. Okay, so reinstall this in the robot. Yeah, just check real quick. No comments. All right. I'm going to do the reinstallation here. Okay. Okay, so it's going to go to the left motor. This is going to go to the right motor. All right, cool. All right. Sorry. phone's about to die. That means it's been almost 2 hours. All right. Okay. Almost not centered. Alrighty. Oops. All right, cool. Put in screws again. All right. Screws back in. All right. Oh, cool beans. That means we got. Oh, I got our stuff installed. Perfect. All right. Let's get a battery mounted. Or actually, even though we don't have the ability to use the LiDAR yet, let's at least get the let's at least get the connections in so we can test whether it'll spin or not. And okay, data connections in. We got the motor connection is in. All right. So the only reason we're doing that is going to spin this around, put that in there. It's not how we're actually going to mount the LiDAR in the end, but it works for testing pretty well. We're going to stick a battery connector through there. And just a little bit of taping just to secure the battery. And we should have the code in from earlier that'll make the LiDAR spin. It won't spin at the right speed, but it will spin at the very least. Why did it do anything interesting? Oh, because we haven't actually connected the battery. That's why. Well, that would change things. All right. All right. All right. Oh, Jesus. All right. Tape didn't work. Tape did work. Tape just wasn't tapey enough. Okay. All right, the LiDAR should hopefully spin up. And it does. Okay, perfect. Now, if we put the robot, let me move the robot to the ground. And we'll spin up. Actually, here, let me grab my phone here. We're not going to switch to battery saver. If we fix, let's rotate, or undo all of that rotation, right? We'll come over here. We'll kick off the remote. We'll pair my controller to my desktop. I have replaced the Bluetooth antennas. And we are connected. We'll connect the controller. And we're up. And we can drive around with the LiDAR. And the LiDAR is indeed spinning. So, we have now finished our well, we don't know if the LiDAR is actually sending it, the robot's actually sending out anything interesting over the LiDAR, but I mean, if the LiDAR is sending, wow, I can't talk right now. If the LiDAR, if the controller is actually getting any data from the LiDAR, but the LiDAR is indeed spinning. So, okay, let me cut this video here and go back to the desktop footage just so I can charge my phone. Okay. Let me meet the Pixel 5. There we go. Okay. How close to empty did we get? 5%. Oh, and I don't have a charging cable in here. Lovely. Okay, I'll be right back. My cable. Get the debugger for the Pi Pico. And let me sit back down. And turn the webcam back on. There we go. Plug my phone in to the high current port. All right. You can see the background of the robot is drivable. And the LiDAR is spinning. The only thing we really have left to test is the servo. Well, regarding hardware anyway. Let me go plug one of those in real fast. Let me turn off the camera again. Yeah, let me plug a servo in real fast. Let me plug the servo that I would actually be using in. It's one of these little micro servos. Oops. Micro servo. It's actually a little hard to do with the robot running because I can't flip it over because I can't grab the LiDAR. Alright, so we'll run the cable through here. Servo's not going to actually do anything at the moment, right? Because it's not programmed to do anything. But we should, if I remember, we set the signal as the top pin, so let's not plug it in backwards. Alright, it's plugged in. Now, let me put again, sorry, I'm going to turn the camera off again. I need to put a servo horn on it. Grab a servo horn, just so you can see the servo move. If we get it moving anyway. If we get to the point of getting it moving. Alright, so, actually, let's write some code to control the servo real fast. Actually, what do I want to do? Yeah, let's write some code that'll control the servo real fast. We'll add another thread that just pans it back and forth, because we have threads, because we have free RTOS on here, right? So let's do that. Let me kill the remote control program, turn the robot off, and then there's
moisture on my desk from the soda sweating. Anyway, okay. I said this would be a short stream, but here we are, almost 3 hours in, watching me soldering. Okay, so the motor is. So the servo, we remember we changed to GPIO 0. So let's. So yeah, we used UART 0 for the I2C, and we used. Wow. Okay, I already had this again. So yeah, we used UART. We used UART 0 over here to receive, and then we used the UART again over here. So we left the couple of we've left most of the SPI pins alone in the event that we want to use an SPI device, although we did restrict ourselves to not that many pins left. But again, this is a prototype board, so it's fine. We don't worry about it. But yeah, so we'll just delete this unused thing, or the no use, and then we'll connect up our servo, and then we'll mark 11 is unused. Yeah, so we freed up 11. So yeah, so now we've eaten up a bunch of the UART 0 pads, but we explicitly used UART 0 over here and I2C 0 over here, so we're good. So so we'll do a couple things. So yeah, let's start with the servo. We'll throw the servo in motor. So we'll say set void set servo set motor tilt position, float position. And in motors, we'll say define. What is define? Oh, I'm hitting keys I don't intend to hit. Define motor tilt PWM as 0. And then what we'll do here is we'll say GPIO set function motor tilt PWM GPIO func PWM PWM set wrap PWM GPIO to slice num motor tilt PWM. This will be, we have to actually figure that out. And PWM set enabled, PWM GPIO to slice num motor tilt PWM. True. Okay, so the wrap. We also might need to set the interval. So here's the thing about servos. They need a pulse. So especially these old analog ones, like the ones I'm using, they need a pulse train at 50 hertz, basically one signal every 20 milliseconds, and it needs to be between it needs a pulse high between 1 and 2 milliseconds long, and then stay at 0 for the rest of that 20 millisecond window. So we only want we basically want the PWM to wrap every 50 hertz, or 50 times a second, or every 20 milliseconds. So by default, the Pi Pico's clock speed is 125 megahertz. So that'd be 125 million, 123, divided by, these are 16-bit timers by default. So that's going to be 65536. So we can see that by default, they overflow, even if, even if you let them go the whole way, they overflow. We build a cat trailer to shuttle cats around. Absolutely, Danish. We're going to build a cat trailer to shuttle cats around. So as you can see, it will the PWM will overflow every 1900 times per second, which means we need it to overflow 50 times per second. So we have to basically do what's called prescale, which is we need to divide the clock by a certain amount. So we're gonna go look at how to in the Pico SDK how to set the prescaler on PWM. So under hardware APIs, there's going to probably be, yeah, that whole thing with clock div. So hardware PWM, and then we're going to be able to say there's going to be a clock div. Okay, set the PWM clock divider in a PWM configuration using fractional 8x4 fractional value. That's really cool. So realistically, if we want, so just to give ourselves a bit of, to make our numbers easier, what we'll do is set the clock to overflow, let's just say 1,000,000 times per second. Or we'll have it, we'll divide 125 megahertz. We want to have a value between, we want, let's say we want the precision of our, because it's a counter, right? Let's say we want let's say we want 1,000 to equal 1 millisecond. We want each tick of the timer to be 1 microsecond. So we would need to divide the clock by 125. So 125 million divided by 125 is 1 million, and then that would basically be 1 million ticks per second into the timer, and we would set the overflow to be at 20,000. Which would overflow at 20 milliseconds. So what we'll do here is I'm going to set the function. We're going to say pwm config set clock div int divider pwm config. Oh, we have to actually change the config. So we'll say pwm get config, get default config. Auto c, here we'll use better names. Auto config equals config, and then we'll say pwm config set clock div integer. We'll use config, and we'll set the divider at 125. And then we're going to say pwm set, or pwm set config, probably pwm initialize a pwm with alright. PWM config set wrap. That's in the config. So set config or set wrap. So as we said, we wanted to wrap at 20,000 because we want 1 to equal 1 microsecond, and if we wrap at 20 milliseconds, that'd be every 20,000 microseconds. And so now we need to be able to set this config. And so that probably means we use, let's see, advanced count return, set clock div. Oh, can we only set in? That's funny. Okay. Config. Okay, you know what? Fine. PWM init. We'll say slice number, which is just going to be this. And then the config is config, and then true to start it. Set enabled. Enable to specify PWM. What does actually that do? What is the implementation of this? Check slice param, hardware write mask. Does this also enable it? PWM, CSR, bool to bit. CSR. Okay, yes, that does turn it on. All right, so set wrap, set function. Okay, so all we have to do here is do that, and then, well, we'll actually do the GPIO set function before we apply the configuration. Probably a better way. Nope, don't delete that. So we've got set motor tilt position, float position. We say auto position equals position. Actually, you know what we can do? We can say So if it's from -1 to 1, we're going to say position times 500 point f. And then, or actually it's position underscore times 500 point f. So that'll scale our -1 to 1 to, we'll just make sure that we don't screw that up. Yeah, auto position is if actually, yeah. So set level speed. Oh, that's fine. That's plus motor dead zone speed times. Oh, okay, yeah. So if position greater than 1 point f, otherwise position less than -1 point f, -1 point f, otherwise position. Multiply that by 500, and then we do PWM set GPIO level. Oh dear. That's motor tilt PWM. That's going to be position. That's going to be uint 16 position plus 1000 or plus 1500, which is the middle zone. So yeah, we multiply by 500. So -1 will turn into -500. +1 will turn into 500. 1500, 1.5 milliseconds as the servo is centered. So plus 500 would be 2000 or 2 milliseconds. Plus -500 would be 1000 or 1 millisecond, and that's the range on servos. So that's good. And so what we'll do here is we're going to create we're going to call this the sweep task. We're going to say void tilt sweep task. Unused void param. Say while 1. We're going to say for float. Oh, geez. Float I equals 0. I less than 1. I plus equal. We'll say we want it to take 1 second to go, or 2 seconds to go. So half the range will go in 1 second. So we'll say plus equals 0.1f, 0.01f. We'll say there's 100 positions, and then we'll say motor or set tilt position I, and then we'll do a v-task delay 10 divided by port tick period milliseconds. Should delay 10 milliseconds, and since we're doing 100 positions, that will be 1 second. And so then we do actually I take it back, -1, yeah, less than 1, and then equals 1, greater than equal to greater than -1 minus. Okay, and that'll sweep it back and forth. Actually, we'll just say 5, or we'll leave it at what we were doing. Minus 1 greater than -1 subtract. Okay, yes, that'll work. Oops, that's not how that works. We do want to hit the maximum, so we'll do that. It is floats after all. And then we need to create there's main task handle. And then we'll say task handle, tilt sweep task handle, x task create, tilt sweep task, tilt sweep task, tilt sweep thread, and then 8 kilobyte stack, null pointer, test task priority, and then tilt Sweep task handle. Okay. And that will create our sweeping thread. And so we'll compile our project. Compile project. Perfect. We'll unplug the phone. We'll plug in the Pico to the debugger. To the debug. I can just get this little connector to plug in. There we go. We'll turn it on. And then we'll flash the project. And the servo is freaking the fuck out. No, it's not. It's kind of doing something. Oh, it's kind of freaking out. Okay. That's fine. We'll figure it out. Interesting. Okay. I less than I plus equals. I do something wrong? Maybe I did my math wrong. Hold on. Clock div int. Clock divider. If the divide mode is free running, other clock sys divided by div, otherwise the divider reduces the rate of events. Must be greater than 1, less than 256. That's perfect. Set config. Set wrap. Wrap 20,000. That should make us expire 50 times per second. Set function init. So PWM. If false, you will need to manually start using set enabled. Okay, well that's fine. What did I do wrong? I mean, it's moving, which means something is correct. But again, I don't know if my math here is right. Set level. PWM level for this GPIO. Right. Okay, did I do something funky? Maybe I did something funky on accident. What did I do? PWM init. Did I do my math wrong? Is that what I did? Well, we can always do the fun thing of, we have a debugger. I keep forgetting, usually when you're doing Arduino stuff, you never think about having a debugger. But with PyPico, we have, all modern microcontrollers, let's be honest. ARM, you have a debugger. This is ARM, but the PyPico, this TM32, debuggers are something you typically have now. But back in the Arduino days, unless you were willing to give up the pins to connect the JTAG debugger, you couldn't get debug. And the JTAG debugger was expensive, and forget if you needed a PIC debugger. So we're gonna say, we're gonna just enter debugging mode. We're gonna put a breakpoint here. We'll put a breakpoint here. Start the debugger. We got a breakpoint. Wow. Okay, we got a breakpoint. What happened? Tilt task set position. Yeah, what happened? What's our position? Position is negative 500. Alright. Oh! Oh, I cast a negative number to a positive integer. Okay, that's what I did. Okay. Fine. Fine. I'm an idiot. Okay, cool. There we go. Mystery solved. Last project, SWD. Let's see what happens now. Ooh. Something fun looks like it happened with the servo. It snapped over to one side. Oi. Now what? What did I do now? Doop. Debug. Breakpoint. Alright. Motor tilt sweep position. Position is negative 500 plus 1500, which means we set in why is it always -1? Oh no. How about we uncomment that? Continue. Continue. Stop. Balancer. Alright. Launch the debugger with no breakpoints. Oh, it's ticking along. Perfect. Alright, alright. But it's not moving by much. It's only moving by about 90 degrees. Not even 90 degrees. Maybe this is an extended range on the input, so let's actually multiply this by 750. And rather than waking up 100 times a second, we'll do plus 0.01, and then just do this every millisecond. Then we'll do file project, flash project. Alright. Actually, just so we can center the servo, we're going to comment out this task. And we're just going to say set motor tilt position at 0, and then vtask delay 1000 divided by 0.2 period milliseconds. We'll do that just to get it to center. Just like put the servo horn on in a centered position. See how much it actually moves. Okay. Interesting. Perfect. Okay, now it's centered. Now we can delete that. And uncomment this again. And then SWD. Perfect. Okay, nice. All right, so let me bring up the camera just so you can see it. So it's not exclusively for my own viewing, right? So as you can see, the servo is sweeping back and forth. So we have servo control off of our chassis controller. We have our LiDAR spinning. And it would move if I turned on the this, or the balance controller, and this is going to be horrible. It's up, and it's going to try to run real fast. Oh, service name not known. Did it not? Oh, there it goes. So, uh-oh. It's not moving. That's probably a good thing that's not moving. Let's power cycle. All right. And let it come up. Connection refused. Connections accepted. It'll be scary. Okay. Oh, nope. Connection refused again. Okay. It's not up yet. Nope. Connection refused. What the heck happened? Why is connection refused? Why would it be refused? Oh, there it goes. Nope, connection refused. What the heck? Okay. I don't know. Why is that? Huh. Interesting. I like that. What's going on here? What is going on here? Why is it refused? Something networky. Alright, we get to run the debugger again, because this is weird. Boop. Boop. Okay. So that's the thing. Connect to Wi-Fi. Con refused. Interesting, interesting. Config thread. Is there a maximum number of threads that can be running or something? Hold on. Maybe let's look in ROS config. Maybe, okay, hold on, let me switch back to the desktop. Maybe there's a max threads that we ran into. Use timers, length, cover routine, no. Like failed number of cores to core. Trust zone, pico time sync. Is there a max threads? I don't remember. I don't remember. Huh. Anyway. X task create. We'll do, because this is a special one. Config task. We'll put one there. Oops. Ah, sorry. Debug. Okay. Servo is sweeping. All right, and we are connected. We'll continue. Balancer client. Yeah. Yeah, okay. Alright, remote control mode. Let me go back to the desk cam. It's probably a terrible idea. But, hopefully. Whoop, yep, there we go. We can drive it now. On the desk, which is bad. Anyway, okay, it's moving. Right? Okay, we got full control, right? We got a LiDAR, we got that, and I did comment out the LiDAR task, so let's see what happens if I put the LiDAR task back in. Which, for reference, all the LiDAR task is actually doing is it reads the UART and then outputs, writes the data coming back to it to the USB console. So we'll do LiDAR thread. And then, let me go back to the desktop. We'll run the debugger. And see, hopefully we get to the res receive thing. We haven't got there yet, though. That's interesting. Yeah, and it's sweeping the servo. We haven't got here. That's really interesting, actually. Yeah, I really wonder if there's a maximum thread count that we're bumping into. Yeah, free RTOS config thread. Thread local storage pointers 5. Maybe there's a special free RTOS max threads. How do we set a thread limit? Or how do we unset a thread limit? Round robin, getting one. How do I? What if I said 10 here? Maybe that'll do something. 8 registry size. Texas. Okay. Stop. Run. Servo sweeping. Interesting. Very interesting. Why is it breakpoint? Oh, I wonder if this is the LiDAR task conflicting with printfs or something? No, that can't be it. That can't be it. I highly doubt that's it. No. But what is our call stack here? Breakpoint. Idle doorbell task. That's just weird. You know, sometimes debugging and embedded stuff is funny anyway. But debug, do that again. See what comes up. All right, cool. Wait, PicoPyBot, run over there. Run over there. I'm gonna click run, and nothing freaking happens. Super weird. Super freaking weird. I mean, the servo's still sweeping, so it's not crashed. I don't like what I'm saying. What is going on? Oh, what is going on? I don't understand why. You know, okay. Well, let's add a auto res equals that, or we'll do auto res2 equals task create, and then printf x task create result. Type is base type. Let's say D. Oh. Long. It's a long. Okay. Which is D. Yeah, that's fine. LD really, but okay, that's fine. Okay, you got debug. We get here, okay, res is -1. What is -1? What does -1 mean? Maybe we can only have so many tasks of the same priority? Okay, so we definitely failed to create the task. That's good to know. So now there's no remote control task. Create returns -1. Okay. Error code. The value must be between. Priority itself is reserved for interrupt handling. The X task. Okay. But why did it fail? Is there like a heap size limit? This is what I get for pulling code out of a minimal stack size. We're just gonna say 8192 here. See if that. I'm just changing random shit, aren't I? That's fine. We're gonna debug this again. Heap total heap size is 128 kilobytes. That's a lot. That's like half the RAM. That's fine. Oh. Oops. That's funny. It crashed. We run out of RAM? That can't be right. That really can't be right. There's no way. We're on a Pico 2, so we have more RAM. So let's up the heap size. All right, red. Oh, and it worked. Okay. That's interesting. So if we upped the heap size, well, we have 512K of RAM on a Pi Pico 2, so on a RP2350. So I upped the heap to be half the memory, so 256 times 1024. We'll put this back to what it was, which is 5. And this is the only thing that we changed, and I just don't know how much dynamic. Well, I mean, we're only starting, 1, 2, 3, 4 threads, right, in total. Why is it using 128K of stack? But whatever, I guess. We'll debug that in the future, I guess. We're not trying to dig into this too much right now. The servo is sweeping. This is running. Yep, and then bind sock address on there. Yeah, it worked. Okay. Print that. That worked too. Okay. Terminal. Client. Yep, and it's able to move with the controller. So, yeah, all right. We ran it out of RAM, or we blew our heap anyway. Okay, interesting, very interesting. Now let's see if we can use the yaw to help us do something, because we're setting yaw rate over here previously. Velocity PID set point control. We don't really need velocity PID right now. Send packet, FIFO, do the thing. We'll change this up. SDA pin, remember we used 12 and 13. 12 and 13. And our I2C dev DMA thing, we were using I2C0. Or we're now using I2C0, right? So, we'll do it at I2C. We don't need any of this tilt stuff anymore. None of the set point stuff anyway. Yaw target, yaw set point, yaw response. That's fine, right? We're only using the yaw. Yeah, let's experiment with this. So we'll do yaw rate. We'll do packet.control. Do we have access to packet up here? No, we don't. Huh. Okay, well, how about... Okay, we won't set that. We'll just keep doing what we were doing before, but we'll disable the ability to set the motor from in here. And yeah. We'll disable the motor setting in there. Oh yeah, we're gonna comment that. Okay, it's fine. We'll just comment that. This, realistically, all we're trying to do here is get the yaw target. Interesting. Yeah, we're not actually really trying to do anything. We just want to get the data out, right? We'll just get the measurements. Tilt P, tilt I, tilt D. Tilt, PID, get set point. Tilt. Orientation is Euler. Yeah, that's all we really want. We're just trying to... We're going to try to reuse some of the tools from earlier to get some of the data in. So yeah, we'll re-enable the IMU thread now. And we'll kick off the debugger. And then in the terminal, we're going to do tools. Oh, something broke. Something broke. I guess. Doorbell. Stop. What else did I comment out that broke things? Oh, yeah. Set up the interrupt. There we go. IMU interrupt. Go to definition, right? Int pin was pin 14. Okay, Pico debug. Breakpoint, it blew up. IRQ in it. Why did it blow up? I don't like that. DMP, do the thing. I squared C. We set all these up correctly. That motor. V-task delay. Set up all of this stuff. This up, right. And if we comment out the IMU task and we run it, it'll probably run fine. But yeah, the moment we try to use the IMU, it's exploding. I don't know why. Did I mix up my SDL SCA pins? No. GPIO 12 is SDA. GPIO 13 is SCL. All right. I2C dev, I2C DMA. Did I do anything wrong in here? Maybe. Who knows? But yeah, now it's running. And then we'll put a breakpoint here. Or enable the IMU thread. Okay. Okay, it's running. Maybe we'll get the IMU and stuff. I'm gonna do Jupyter notebook here. Maybe let me check my firewall settings here. Sudo UFW status. Make sure that the correct. Okay, firewall's turned off. Alright. Do this. We're gonna run. Is it Shift Enter? I think. Non-existent. It's either due to a misspelling. Oh, come on. Make sure that I didn't change the notebook. Yeah, Jupyter notebook. Okay, loading Boca. Boca loaded, cool. Okay, glyph refers to non-existent column name. This could be due to misspelling. Why velocity error? Oh yeah, look at that. Velocity error. Velocity target. We don't set velocity error though. Why did I... Why is there a VE line? What does that even do? Yellow. Interesting. Okay. It's up. I don't know if that means it's working, but balancer. We can say the sweep is running. Motion packet. SQ send, state packet. I could say SQ receive. All right. Let's try that. Debug. Why is that a thing? There's no way this is breaking again. What the hell? What is going on here, huh? If I come to the LiDAR task, maybe that's what's causing all my woes. Interesting. It seems to be running. And execute receive. Look at that. Okay. Doesn't do it again, but... you know... see what happens. Oh, look at that. Oh, interesting. Interesting. Get FIFO count. What's the packet size? Oh. Interesting. Interesting. Maybe it's not working. Okay, I have to do more debugging on this, but it looks like the IMU is not coming up. Or to a certain degree it's not coming up. The DMP stuff doesn't seem to be coming up. But we get... we do get some stuff, right? Yeah. Because otherwise the DMP init would have failed. So we're getting quite far. Yeah, optimized out. 5, MPU interrupt status. and 24. Interesting. So interesting. So something's wrong with the FIFO, which that's fine, I guess. It's not great, but it's not. It's something's running. And yeah, that blows up in my face. Okay. I like that. I like that. View task delay. If I just, if UART's readable, do a thing. UART get C. No, 10. If I did that, what if I didn't do anything other than just spin in a loop and read a UART? Breakpoint. Why? Why though? Feels like I'm still having trouble with interrupts. So I'll leave this here. It's already, stream's already almost 4 hours, right? So either way, the goal today was to get, what do you call it? The goal today was to get the board put together. That was to finish the soldering on the board, to get that into the robot, and clearly some things are almost working, but or the IMU is the only thing we have a problem with. We've got the servo sweeping, we've got the LiDAR spinning, we've got so obviously a lot of stuff is in fact working. So yeah, let me start this up again. And comment out that. Let me kick this off. And switch over to the desk cam. So yeah, obviously the LiDAR is spinning. Our little servo there is sweeping. If I... Oh, yes. Why did it stop there? Run that, it connected to the Wi-Fi. If I do, if I run the balancer client from before, and it connects, you can see that I've got, the robot can move. We got the LiDAR, so a lot of stuff we got put together today. So yeah, in the next stream, which will be Tuesday, we'll do the 3D modeling for all the bits that we need to hold stuff into this robot. So we'll be making the battery mount that'll hold the battery under the frame. We'll be making the Raspberry Pi mount, or more realistically, probably just importing the Raspberry Pi mount from another project. We'll make the thing that holds the LiDAR. We'll make a thing that holds a camera. But yeah, we'll make all of our 3D printed parts. And if there's any time left after that, which will going by precedent, probably won't be. So next stream's about 3D printing. That'll be Tuesday, and then yeah, and then we'll do that, and then after that we'll start on software. So let me switch back to my desktop here. So thanks for tuning in on a random Thursday to finish this up, and I hope you all have a good evening, and thank you for watching.